In this problem, we have to do a vertical order traversal of a binary tree, and this has been asked quite a few times in the interviews of Facebook and Amazon, and also a few times on Google, Microsoft, and Apple. So let's first understand the problem. So here we have to traverse it vertically. So we have already seen some of the traversals like level order, in order, pre-order, post-order. So here we will traverse vertically. So first start from leftmost column. So we have a notion of column, and we will call this as level or row. So we will start from leftmost. There is no element to the left of 4, and we will shortly see what is the notion of column. So we traverse 4 first, and this ordering is important, even this order of vectors, and within that vector the order of elements, that is important. Then we traverse 2. So you can see 2 here. Then we have 1, 5 and 6. And why these are together? So this means they are in the same column, and we will see why this is so. Then 3 and then 7. So roughly you can see that we are traversing from left to right, and within a column we are keeping the top element first. So we are starting from top to bottom. We are looking from top to down. So whichever is at the top we will print first or include in the result first, then the element below it, and then below it. So we traverse from left to right and top to bottom. So now let's define the notion of columns. So root is at column 0. So this is the middle. So if you have drawn these Cartesian axis, this is the 0th column or y, and then this side we have positive, this side we have negative value of x. So exactly same, we have to think of root as the pivot here. So root has a column number of 0, and when we go left, its column is 1 less. So this column number is -1. This column is -2. And when we go right, we increment the column. So this column was 0. For 3 it will be +1. For 7 it will be +2. And from 3 we are going left. So decrement 1. So it becomes 0. And here from 2 we are going right. So increment 1. So it becomes 0. So you see that there are 3 elements with the same column, that is 0, which are 1, 5 and 6. And we have kept here 1, 5 and 6, and it's not because 5 comes first in this row, it's because 5 is smaller. So first we will arrange them based on a column clearly. So this -2 is the smallest column, so this 4. Then -1 we have just 2, so there is no confusion. Then we have 0. In 0 we have 3 elements, and we arrange them based on their row number. So when we have multiple elements, see which is at the smallest row number. So 1 is at row number of 0. These elements are at row number 1. These are at row number 2. So these are same as levels, and row is increasing from top to down. So here 1 is the clear winner. It's at row number 0. So we put it first. Then 5, 6 both are at row number 2. So which should be put first? So when multiple elements have same row and column, we compare their values. So 5 is smaller, so we keep 5 first. So if we had 6 here and 5 here in the original tree, then still the result will be the same only. It's not because 5 was coming first. So this is the basis of comparison. Now I hope the problem statement is clear. So then the column number is 1. So at 1 we have just 3. Then column number is 2. So at 2 we have just 7. And this is the result. So how we will build this result? So we will traverse the tree, and there are multiple ways of traversing. You can use BFS approach or DFS approach. Here we will use DFS approach since that's more natural and recursive way of traversing. So we will start traversal from root. So root is 1, its row number is 0, its column number is 0. And we will maintain a global cache. And this cache, we will keep track of what elements are in a given column. So ultimately we should have -2. So here key will be column number, and value will be a vector of or a list of all the elements corresponding to that column. So a vector of vectors, and each element we will store row and value. So this is the structure of this cache. Initially it's empty. So we start from root. We get a column number of, this is row, this is column, and this is node. So row number 0, column number 0, we check the cache whether this key is present or not. It's not present, so we insert it, a new key, and this element 1 at row number 1, and the value is 1. Then it will call DFS on its left. Its left is 2. So this is not the value 2, this is node 2. It has value within it. So 2, and its row number is 1 more than parent, and column is 1 less since it's the left child. And it will also call DFS 3, row number 1, and column number +1. Then this 2 will call for 4 and 5. So here in DFS, what we will do, in DFS we will compare this column whether this is present in cache or not. If it's present, we will just append this value, current node's value, into it along with row number. If it's not present, we insert a new key and one element here. So for this call, -1 is not present, so we insert -1, and its row number is 1 and value is 2. Then this will call DFS on 4, row number 2, column number -2, and DFS 5, row number 2, column number 0. So in this call, we will check whether -2 is present or not. It's not present, so we will insert it, row number 2, value 4, and then 0. 0 is already present, so we just append it to it, row number 2, value 5. And then we come here, +1 is not present, 1, 3. Then this will call for 6 and 7. So DFS 6, row number 2, value, and column number 0. Again 0 is present, so just append it to 6. And also DFS 7, 2, row number is 2, column number is 2. So 2 is not present. So now this DFS call terminates. And one more thing we will do, we will also keep track of what is the smallest column that we encountered in this entire traversal, and also largest column. So min call equal to -2, this is the smallest column number, and max call equal to +2. And when this traversal completes, we will have this cache. So let me write this again. So I have rewritten this cache. Now what we will do, once this cache is built, so let's write our main function. Let's call it vertical order traversal, and we are passing root. So here what we did DFS on root, row number 0, column number 0, and this was built a cache. So cache is now built, which is this one. Cache is built in this DFS call in this fashion, what we saw here. And then we have min C and max C. So this we have after this DFS terminates. Then what we need to do, our result should include in this format. So first the smallest column number, then next one, and so on in increasing order. So we know the min and max call. So what we will do for C equal to min C to max C, we get the elements corresponding to this column from this cache. So initially C will be -2. So for -2 we have this value. So when we sort it, there is just one element, so nothing to sort. So it will be 2, 4. And in this 2, 4, first one is the row number, second one is the actual value, and we are just interested in value in the result. So we fetch this 4, second element, and result which was empty, we insert this 4. And this is the only element, so just one element. Next, C becomes -1, so we go here and get -1. Again one element, nothing to sort, so get the second value, put it in a vector and insert in the result. Then C becomes 0. For 0 we come here. We have now 3 elements. So now we need to sort. So first we will see the row number. So smallest row number comes first. So clearly 1 is the winner here. It has a row number of 0. So it comes first. But for 5 and 6, row number is equal, 2. So which one we should write? Whichever value is smaller. So 5 is smaller, so we write 5 first. And as seen earlier, this Even if 6 was here and 5 here, still we would have written 5, 6. So here the basis of comparison is the value itself when they are in the same row, and then 6. So we will just extract the second element of this pair. First is row, which is just used for comparison, sorting, and nothing else. We are just interested in value. Then column number 1. So we come here, it's 1, 3, just one element, nothing to sort. Then C becomes 2, max C is 2, and we come here 2, 7, nothing to sort, and we return this. This is our final result. So hope this is clear. So let's write the code for this in C++ and Python. I will skip Java for this exercise. So this is our main function. We will need to define a DFS also. So first, result is a vector of int. So if root is null, then return the empty result. Else we will keep one cache. Key is the column, so it's int, and then the value is a vector of pair of row and actual value. So row is int and value is also int. You can see the value is int. Let's call it cache, and then min c equal to 0, max c equal to 0, and then we will call DFS on this root, row number 0, column number 0. Let's define the DFS first. And then we need to use this cache inside this. So let's pass this by reference. And we will also be updating min c and max c. So row number 0, column number 0, and cache, then min c, max c. And when this DFS terminates, we should have this cache, min c, and max c ready. So what we should write in DFS: if node is null ptr, then we return, and then we check. This is the column that is passed to us, so either it has been already inserted in the cache, some elements corresponding to that column, or this is not present. So if it's present, then we will simply append it to it. So this cache will return the vector of elements, so we will append it to it the current row number. So first element is row number and second is the value. Else this was not present here, so insert it. Both are same thing, just handling. If the key is not present, we cannot directly access using this, so that's why this check is required. So we insert the column number and then row and value, and then we update the min c, and we will recursively call this on left and right of this node. So if this was leaf node, it will be null, so it will automatically return from there. So row number will be one more than the current node for its children. Since it's left, column number will be one less. For right, column is one more. So when this DFS terminates, we have these things ready, the cache, min c, and max c. So what we will do, c equal to min c, c less than max c plus 1 plus plus c, We can also sort this in place. We don't need to make a copy here. But for simplicity, I'm making a copy. We don't need, even we can pass this. So let's use this only. And then this is a vector of pairs. So we need a way of comparing it, and the comparison is based on row number, which is the first element. And if rows are equal, then based on second number. So our comparator will take two pairs. So this means that if the first value of this first pair is less, then put P1 first. But this is not the only criteria. If this is not true, then we have to also check if P1 dot first is equal to P2 dot first, that is rows numbers are equal. Then if P1 dot second is less than P2 dot second, which is the actual node value, then we put P1 first. If none of these cases are satisfied, put P2 first in the sorting. So this cache C is now sorted. So what we will do, we will have a vector that we want to insert in the result. This should be vector of int, since in the result we expect vector of ints, that is the actual node values and not the row number. So we will extract the second element from this vector and put it into this vector. So we are getting the second, that is the value, and pushing it to this vector, and finally we insert it into result. And after iterating through all the columns, we return the result. Line number 20. 16. And this works, but the answer is wrong. The comparator is wrong. P1 dot first, it should be P2 dot first, and then first, then second. So we were comparing apples with oranges here, P1 dot first and P2 dot second. Now it's correct, and the solution is accepted. And the solution is around better than 93.71%, and it's very close to the best one. So what is the time complexity here? So here we are clearly iterating through all the elements. We are traversing this complete tree. So clearly ON is there at least. But after that traversal, we get this cache, which we need to sort individually. So the sum of all the elements in all the elements in this cache is same as the elements here. And at max, let's say in some case, we have elements come in order of n in these. So sorting will take n log n time. And it's just we are splitting the complete n into different n's like n1, n2, n3 and sorting them individually. So overall it can take n log n time, but in most cases it should be, let's say we divide into 10 parts, then n by 10 log n by 10. So it will be n log n only. You can do more time complexity analysis, but it looks like n log n here. Now let's write the same thing in Python. So we will have result, which is a vector or a list, and if root equal to none, then return result, else we will have a cache, which is a dictionary. And then we will define our DFS function. And here we don't need to pass these this cache and min and max, since we have added this to the self. So if this column has already, if we have already inserted sub elements corresponding to this column, we will simply get that vector and append to it this value also, the row and the current value. Else we are inserting it for the first time. So cache C equal to you can also initialize this with empty list corresponding to C and then just append it. So both are same. And this should be here. And then we call DFS on its left, and its row number will be one more and column number will be one less for left. For right, again row is one more, column is also one more. So this DFS terminates, and when this completes for this tree, then we will have this min C, max C and cache ready for us. So we just need to do the sorting. So for C in range, so this C will take a value of -2 first for our example, then -1, 0, 1, 2. So we pick the vector corresponding to this column and sort it, and the basis of sorting will be the first value, which is row number, and then second value, which is the value itself if the row numbers are same. Then we will extract value from all the elements of this vector and push it into this vector, which will be pushed to the result. So we have not called the DFS itself here. We should call DFS on root, row 0, column 0. So this was missing. Let's run it again. And the Python solution is also accepted. And here also we are good, but not that great. We are at the peak of the distribution. So I hope the solution is clear. The main crux of the problem is in building this cache when we are traversing. So when we go left, the column number decreases by 1. When we go right, column number increases by 1. And we are keeping track of what all elements are in a given column number for all the columns. And then we finally sort this based on row number followed by value of the elements.